Thank you, Pallavi. Thank you for the invitation, and thanks a lot for iLEAPS framework for such invitation. So today I will speak about remote sensing in the framework of urban planning, how to use remote sensing for urban planning in the context of climate change and air pollution issues. So as you know, ambient air pollution is a major public health issues leading to more than 4 million deaths worldwide in last decade. In cities, citizens are exposed to more than 200 classes of air pollutants, and the most harmful for human health and ecosystems and biodiversity in general are tropospheric ozone, fine particles, and NO2. A billion of people are exposed to level of air pollutants above the World Health Organization air quality guidelines for human health protection. First estimation, by 2050, ambient air pollution will lead to almost 7 million premature deaths. Just state of the art about air pollution in cities, looking at PM 2.5. So between 2000 and 2019, in urban center with more than 50,000 inhabitants, we have a clear improvement in North America, Europe, Western Africa, Eastern Asia, with the most important improvement in the US. While we have a degradation, and the most important degradation is observed in South Asia with an increase of more than 3% per year of PM 2.5 mean concentration.
Dr. Pierre?
Yes.
Yeah, sorry if I may interrupt, because you are not sharing the screen.
You cannot see the screen?
No. No, I think you haven't started sharing.
Hello, one moment. I can.
Yeah.
Now.
Yeah.
Now it seems okay.
Now we can see, but it's not in the. Yeah.
Yeah, it's fine.
We can also see your next slide. So.
Okay, so I can because I have two screens. So one moment, I can share this one, and now it seems
yeah.
Okay. Sorry.
That's okay. I just thought that you were giving an introduction. So
okay, so maybe okay, I can see just to show you. Okay, so this is introduction and context about the number of deaths due to air pollution. So for PM 2.5, so at a global scale, we observe a decline of PM 2.5 almost 0.2% per year between 2000 and 2019, and 65% of cities show an increase of PM 2.5. Looking at NO2, so we have degrees of annual mean concentration, in particular in Europe and in the US. While we have a degradation and an increase of NO2 concentration in South America, Africa, Middle East, and the highest increase is observed in South Asia. Except in the US and Europe, the spatial distribution of trends is widely heterogeneous. At global scale, NO2 exposure increased in cities, and 71% of cities show an increase of annual mean concentration. For ozone, tropospheric ozone, so we have an improvement in Europe, in the US, but also in southeastern China and Japan. And we have an increase of mean ozone concentration, in particular in South Asia and in India. At global scale, the ozone mean concentration increase, in particular due to the lower ozone titration by nitrogen monoxide, sorry, while the summertime ozone max concentration increase in 74% of cities. So air pollution, but also urban heat island and biodiversity loss are major problems affecting cities. As you know, urban trees can provide many benefits. For instance, air pollution reduction, urban heat island mitigation, but also biodiversity conservation. And all these benefits are positive and provide benefits for citizens for the improvement of citizen well-being by, for instance, preventing mortality and morbidity. Morbidity is hospital admission, in particular for cardiovascular and respiratory disease. To overcome urban challenges, efforts for optimizing urban greening are needed. This is why many local authorities, government, but also, for instance, in Europe, European directives ask municipalities, in particular municipalities with more than 20,000 inhabitants, to provide and to develop an ambitious urban greening plan. This is why for creating healthy and green cities, one colleague of mine, Cecile, introduced in 2021 the 330-300 rules. In particular, everyone should see at least 3 trees from their home, school, or workplace, living in a neighborhood with more than 30% of tree cover and within 300 meters from a high quality public green space. Why? Alors, 3, because view of greenery from home is associated with better mental health, psychological restoration, and fever medication. Regarding the 30%, living in a neighborhood with more than 30% is also associated with reduced local temperature due to the cooling effect of trees, mitigated urban heat island, but also prevented death and morbidity, in particular for cardiovascular disease. Access to greenery within 300 meters around home is associated with resident well-being and also with social interaction. And this value of 300 meters is recommended by the World Health Organization. This is why this rule is step-by-step implemented in worldwide in many cities, like in Barcelona. However, urban planners and decision makers lack tools to quantify ecosystem services delivered by green space and by urban trees. And also finding appropriate area for greening is cited like a primary barrier to implementing an ambitious urban greening plan, where to plant, which species you have to plant. For that, we can use remote sensing and in particular very high resolution satellite imagery like Pleiad or Worldview with a spatial resolution of between 30 and 50 centimeters of spatial resolution using 4 or 8 spectral bands, multispectral bands, and panchromatic band. Coupled with geographic information system, Python package, OpenStreetMap, and using random validation classification algorithm like random forest. So geospatial tools can be used to detect, classify, and map individual trees in public and private lands and green spaces. Can be used to map ability or not of tree to reduce air pollution, map compliance with the rule 33300, map areas prone to urban in Thailand in order to prioritize where you have to plant, and map open area available for greening strategy. So we develop geospatial tools and different algorithms, and we prototype these tools in 5 different cities: Valencia in south of Spain, Aix-en-Provence in south of France, Florence in Tuscany region in Italy, Bucharest in Romania, and Kaunas in Lithuania, with different urban cities, environmental condition, and representing different geographical region. For that, so for the individual tree detection and classification, we implement some algorithms. So using very high resolution multispectral imagery, Pleiad or worldview, we perform pre-processing data like with a pan-sharpening approach, using a stepwise masking using the NTVI index, the tree canopy segmentation based from using the municipal tree inventory, the public trees, namely managed by the municipality. So now I can explain step by step. So for the individual tree detection, so we use, in our case, the world view satellite imagery. The optimal period is June, July in our latitude, because if you wait September, sometimes you have the senescence of trees, and the trees are different colors, so it's not easy to detect and to classify tree species. So in our case, we use the world view with 8 multispectral bands of 2 meters of spatial resolution and 1 panchromatic band with of 50 centimeters of spatial resolution. Very important, when you select satellite imagery, the cloud cover should be lower than 2%. So in order to have a good view. So first step is data pre-processing using the pan-sharpening approach. Pan-sharpening is merging high-resolution panchromatic imagery with lower resolution multispectral imagery in order to obtain a higher pixel resolution, like you can see on this figure. Second step, so we are able to dissociate and to categorize vegetated and non-vegetated area, namely by using the NDVI index. So in the case of Aix-en-Provence in south of France, the value, the pixel with the NDVI value higher than 0.40 is classified as vegetated area. If you have a lower value, it's classified as non-vegetated area. After that, we have the step for image segmentation. So using the watershed algorithm, we are able to delineate the tree canopy with pixel of the same similarity. After, we use the public tree inventory as a ground truth samples. So we map with a spatial join between the municipal tree inventory and the segmented canopy. And for each canopy, we know which species is. And we use this data set as a training sample. So in particular, we use 70% of the data as a training sample and 30% of the data for validation for classification. So when we have the canopy, the delineation of the canopy, we use the gray level co-occurrence matrix, and for each canopy, we calculate different attributes. So the texture-based attribute. So first, we have the spectral signature of each canopy, and in parallel, we have the textural signature of each canopy. So for that, we use the Aralic texture-based attribute. Aralic texture-based attribute are like anisotropy, similarity, or correlation, etc. And we calculate for each canopy, so this texture-based attribute and spectral to have with a different canopy to have an average signature for each dominant tree species in CT. So, for instance, in Aix-en-Provence, so we are able to detect 22 dominant tree species, representing more than 90% of the total number of public trees. So we used the municipal tree inventory as a training data set, with 70% for training and 30% for validation. And at the end, for each canopy, we have 16 texture-based features and spectral signature. So at the end, we know for each species, you have such signature. And after that, we extrapolate and we are able to detect all similar signature over the satellite imagery in public and private lands. So for the assignment of object to different classes, namely the plant species classification, we use the random forest classification algorithm. So, for instance, on this figure, you can see the different canopy we map and the associated dominant tree species. So we are able to detect and to recognize Acer species, Aesculus species, Cupresius, Ficus, etc. But also we are able to dissociate and to distinguish turf, for instance, for the stadium on the top, and the synthetic turfs. So in this case, we are able to dissociate the synthetic turfs from the green cover, for instance, calculation. So on this figure, so we can map the green cover at city scale, and we can provide to municipalities a full tree inventory, public and private. So in our case, in Aix-en-Provence, we have detected 414,000 individual trees, and 85% of trees are on private land. This is very important because the public trees managed by the municipality represent less than 15% of the total of trees. So for carbon footprint calculation, for instance, or if you want to estimate the impact of your public and private trees on air quality, if you use just the public trees provided by the municipality, you have a very large underestimation of the impact on air quality. So in Aix-en-Provence, so we have a green cover more than almost 40%. So this is Aix-en-Provence is a green city, and the dominant tree species are Pinus, Celtis, Platanus, Cypress, and as many current typical trees in south of France. And for each tree species, we are able to calculate accuracy, producer and user accuracy. And so, for instance, for Tilia species, the accuracy is over 96%. Now we have the full inventory of trees at the city scale, the location, the species, and we are able to estimate the impact on air quality. So as you know, you have deposition of particulate and gaseous air pollutants on plant surface, so on leaves, needles, trunk, branches. So we are able to estimate the quantity of air pollutants removed by dry deposition. Also for CO2 and carbon stock estimation. In parallel, some tree species emit biogenic volatile organic compounds like isoprene or monoterpene, leading to ozone formation in particular. So we are able to estimate the potential ozone formation for each species. For gaseous air pollutants, you have the stomatal uptake. So through stomata, an amount of air gaseous pollutants and we are able to estimate the quantity of gaseous pollutants removed through stomata. So for that, we used some model like those model based on environmental conditions, so the air temperature, the relative humidity, the global radiation, and the soil water content. This is a very important factor for the ozone uptake, for instance. So when you have the map of canopy, the leaf area index, the species, and also using the floor tree model, as I explained just before, we are able to map the impact of each individual trees on air quality. So for that, we calculate the species-specific removal rates for more than 200 tree species. This is an example of the impact of tree canopy on PM10. So it's per square meter and per year. The impact on NO2, so the quantity of NO2 removed by a tree canopy. For CO2, and for ozone. For ozone, it's particular because you can see you have some red part. This is when some species formed more ozone than removed. So the balance is positive. So some species degrade air quality by forming more ozone. This is the case, for instance, for eucalyptus or for quercus species, many quercus species. So in red, you have some part with quercus. This is a quercus ilex is a typical in south of France. So and you can map using the satellite imagery, and you have a short video showing the canopy impact on air quality. This is the quercus forest. Alors, now Okay. The computer is no, you cannot see.
We can see your screen.
Yes, but I guess the video stop.
Okay, okay.
So okay, so one moment, I can start again. No, no, I can. Okay, I can try again. No, PowerPoint is blocked. So one moment, I can start again. Sorry. Can you see?
Yeah.
Yes.
Okay, sorry. Okay, so at the end, so you have a map of the removal capacity of private and public trees at city scale. So in the case of Aix-en-Provence, so about 414,000 trees have eliminated in 2023, 225 tons of ozone, 9 tons by formation, and removal 234 tons. 41 tons of NO2, 97 tons of PM10, and more than 16,000 tons of CO2. So in order to have an idea, I convert such removal, such amount using the emission of private cars in France, for instance, with an average of 2,200 kilometers by year during the year and an average speed of 70 kilometers per hour. So, for instance, for NO2, all trees in Aix-en-Provence removed the equivalent emission of 6,600 private cars. So now, so we can use satellite imagery and geospatial tool for the compliance with the 330-300 rules. For different components, so 330 and 300, we need some data, building data, individual tree inventory, and for the component 3, so I will explain, we count the number of trees around each house, each workplace, or each school. For the component 30, so we define neighborhood using a buffer of 500 meters, and we calculate the tree canopy percentage for each neighborhood around each house. And for the component 300, we need to know to have the road network data in addition to the building data and green space data in order to define and to calculate the distance between the entrance of each house and the entrance of each green space, public green space, in order to know for each house, workplace, or school if you are compliant or not with the 330-300 rule. So data collection. So for the building, it's easy. So we have access to all type of buildings, house, hospital, factories, etc., school, using vector data. You have such information in QGIS, OpenStreetMap, and we use a Python package for OpenStreetMap. For the road network also, so in order to calculate the pedestrian road between green space and house, we use the QGIS and OpenStreetMap data. For the individual public and private trees, so we use the previous approach methodology established to detect individual trees, but also to calculate the tree height, because we consider only the trees taller than 3 meters. So for that, we use very high resolution satellite imagery. To calculate the tree height, so we use tree stereoscopy satellite imagery. So the satellite imagery with 3 different angle view. For each tree, so we are able to detect the maximum height, and we are able to calculate the canopy height by subtraction between the digital surface model and the digital terrain model. So we have an accuracy about 60 centimeters using the tree stereoscopy satellite imagery. So around each house, so we create a buffer of 25 meters around each building, and inside we detect the tree taller than 3 meters. Or why 3 meters? Because usually we use 5 meters. We consider adult trees from 5 meters. But in cities, you have many exotic tree species and the shrubs. So we decided to use a threshold of 3 meters to define and to detect all trees. So within each buffer, we detect all trees and we count the number of trees taller than 3 meters using GeoPanda, for instance, and QGIS. For the component 30, so around each building, so we create an egocentric buffer of 500 meters, and we calculate with the previous approach, we know exactly the canopy. We have the delineation of each canopy, and we calculate the percentage of tree canopy cover within each buffer. The most important is for the component, and most difficult is for the component 300. So we have to define first the green space. So in our approach, we define a high quality green space with the area over half hectares. Free access, very important, because if you consider the initial definition for this rule, golf, for instance, is included. But we had a criteria of free access. So we don't need to pay to spend time in a green space, and public. So using OpenStreetMap, QGIS, you have the location of each green space in cities. After that, we establish the pedestrian road network between the entrance of each building and the entrance of the green space. For that, we use GeoPanda and OpenStreetMap because it's important. You can live very close to one green space, but maybe by walking, it's more than 300 meters. So for each building, we calculate the distance from each building and the nearest green space by following the pedestrian roads. So this is a summary. So for all buildings, all needed information. So the buildings, the individual trees, public and private, the green space, the tree canopy, the walking road nodes, and age in order to calculate the pedestrian distance. So some example in Aix-en-Provence, 68% of buildings are compliant with the component 3, while only 38% of buildings are compliant in Florence, in Italy. For the component 30, 94% of buildings are compliant with the component 30 in Aix-en-Provence, and only 10% of buildings are compliant with the component 30 in Florence. For the component 300, it's more difficult, in particular in typical city in south of France, it's a Provence architecture. So with a narrow street, so it's not easy to build and to create new green spaces, big green spaces. So in Aix-en-Provence, only 27% of buildings are compliant and 41% in Florence. So at the end, we combine all for the 3 components, and only 4% of buildings are not compliant with non-component. 22% of buildings are compliant with at least one component. 56% with at least 2 components, and 18% with 3 components. So 18% of buildings in Aix-en-Provence are compliant with the full rule 330-300. 37% with no component, 40% with 1 component, 19% with 2 components, and only 4% of buildings are fully compliant with the rule in Florence. At the end, so we are able to calculate, for instance, to dissociate, for instance, for 1 component in Aix-en-Provence, 0.3% of buildings are compliant with the component 300, while almost 20% are compliant with the component 30. So as I told you and show you previously, Aix-en-Provence is a green cities. And for each building, you have all information. So if the building is compliant with the component 3, 30, or 300, the number of trees you can see from this building, the canopy cover within the 500-meter buffer, and the distance between the nearest green space. So I can try to show you again a short video. So you can see for each building we are able with a color scale. In red, the buildings are not compliant with non-component. In green, you have the buildings fully compliant, and in yellow and red, compliant with 1 or 2 component. I don't want to stop before the video, so. Okay. Okay, so now we can use also the satellite imagery and geospatial tool in order to calculate the tree canopy cover. I want to show you some result about a new study regarding the tree canopy cover in European cities with more than 50,000 inhabitants in 744 urban centers. So we use the Landsat-derived tree canopy 8 change dataset established by the University of Maryland. And in this dataset, we are value for between 2000 and 2019 of the yearly estimates of canopy 8 with a very high resolution, spatial resolution, 30 meters of spatial resolution. So we use such a data set to calculate the per pixel canopy coverage, so covered by branches, stem, and leaves in all cities. And so we detect trees taller than 3 meters, and we calculate for each pixel the percentage of tree canopy cover. And we apply the non-parametric mental Kendall test and SEN method in order to detect and estimate the trends magnitude of using this time series. So the urban tree coverage is almost 90% over the study period 2000-2019. With, I guess, the proportion of urban tree cover in Scandinavian countries like in Finland, but also in Switzerland and Belgium. While we have the lowest proportion of urban tree cover in Malta. So Malta is a small island close to Tunisia, between south of Italy and Tunisia, Kosovo, and in Romania. In Europe, so we have an increase, in particular, we have an increase of tree canopy cover in cities, almost 0.22% per year, but we observe a decline, in particular in Northern Europe. For instance, a decline of 0.62% per year in all cities in Finland. The highest increase is observed in Romania. And we apply for each cities, we establish a linear mixed model in order to evaluate and to estimate the impact of tree canopy cover on air quality and after that on mortality. So for each 5% increase of tree canopy cover would reduce the ozone max, daily max ozone concentration by about 1.2%. And we reduced the annual PM2.5 and NO2 mean concentration by 2.8 and 1.4% per year. So using the World Health Organization methodology and the RQ approach using the relative risk values, we calculate the number of deaths due to air pollution in each cities. And we correlate and establish a mixed linear model between the tree canopy and the mortality. If you increase the tree canopy cover from the current situation, the current condition, so the year 2019, to 30% as recommended by the European legislation, for instance, you potentially reduced by 9.5 deaths per 100,000 people. So in this table, so you can see, so the number of deaths due to air pollution for the year 2019. And we calculate the difference between the number of deaths in 2019 with the current condition and with the hypothetical no tree scenario, or 30% of tree canopy cover at city scale. And if in all urban area, European urban area with more than 50,000 inhabitants, you increase the tree canopy cover from the current condition to 30%, you will prevent almost 12,000 deaths every year. While if you cut all trees and if you remove all trees in cities, you will increase the number of deaths due to air pollution by almost 25,000 every year. So if you increase the tree canopy by 5% points in the urban centers, you will reduce by 2.4 premature death per 100,000 inhabitants, representing almost 3.6% of air pollution related mortality annually. So in conclusion, so you can use OpenStreetMap data Python package in particular by detecting the entrance of each public green space and each building. We can use the very high resolution satellite imagery in order to have good detection and identification and classification of individual trees and shrubs for dominant trees species, I mean. Geospatial mapping and satellite-based approaches are instrumental in helping cities to develop a resilient and appropriate climate-neutral urban greening plan. Such tools can provide a roadmap for identifying priority areas for greening, in particular in densely populated cities like Florence, and where you have to plant to mitigate, to maximize the benefits provided by urban trees, but also to mitigate, for instance, the urban heat island effect. Living in neighborhood in areas with more than 30% of canopy cover is associated with lower premature death, in particular due to cardiovascular and respiratory disease. And the tree planting program must target not only public spaces like streets or parks, but especially private spaces like residential or institutional yards. And citizens play a pivotal role in urban greening governance because most of trees are growing in private lands. So thank you so much for your attention.